Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, in the last session we discussed lumped circuit model of the spacecraft. So, using the equivalent circuit model, that is the capacitor, we were able to compute the transient behavior of the potential, means how the potential is developed from 0 to negative voltage and what is the time taken for the spacecraft to get an equilibrium potential. So, this is very essential because whenever the potential is built up, how it is built up, it is essential to know, and what is the voltage, what is the potential it is reached, what is that value. So, that we can compute mathematically, that we have shown. And then we discussed different types of spacecraft charging, that is the surface charging, and surface charging means the absolute charging, then differential spacecraft charging, then the internal or bulk, or it is also called the bulk dielectric charging. So, these are the things we discussed. Then we discussed what are the effects of the spacecraft charging, namely how the these electronic systems it can get affected by the, or it can malfunction because of the spacecraft charging and the discharging. Then how the the spacecraft charging can a charged spacecraft can create problem, or it can give the misleading result of the scientific data on the space environments when a satellite is used for measuring the the different whether it is the radiation level, what is the the electron count, all this thing. If you want to do it using the instruments, onboard instruments, they need to be the spacecraft should be clean, it should not be a charged spacecraft. So, these all are the things we discussed in the last session, and in this session we will be discussing what are the means, what are the way we can design the spacecraft, or what are the mitigation techniques, and the mitigation techniques will include whether how you design it, how you do the testing as well as the inspection, and what are the mitigation studies we will discuss. So, in general I can of course, this whatever I am going to tell, this is a general this mitigation strategies for the spacecraft. It is applicable to all the environments. So, you need to know what is the source of the problem, means you identify at the design stage that which component or what are the things which can create this type of, suppose as for example, we are considering the spacecraft charging. So, what is that? If it is a something like an ungrounded the components or isolated components, or maybe this the dielectric is conductivity is very poor. Actually, we need the dielectric, not a perfect dielectric. So, these are the things you need to be that is the spacecraft designer, he has to know, that is what is the source of the problem. So, then what will be the effect, that is the ESD. Suppose the ESD happens, who is the victim, what is the victim? Suppose ESD, if the circuit is the victim because of the ESD or the your electronic communication system, it can be a TTC or so all those things it need to be known at the design stage. So, it means that you determine the threat that is applicable to that environment. Again, where is the satellite, whether it is a polar satellite, means low earth orbit polar satellite, or it is a medium earth orbit, or it is a. So, depending on the where the satellite is there, which orbit, accordingly the environment will be different, and you have to consider the what are the what can be the risk. So, the assessment of the risks is important to. Then you have to implement the measures to mitigate the threats to an acceptable level, because you cannot eliminate it, but whether my spacecraft system should work. So, up to that the performance should be an acceptable performance. So, in order to do that, the system or the subsystem designer or the mission designer, what they do, they demonstrate it through first the design practices. So, there are the design guidelines and there are some well defined the design practices which need to be taken. Then once the design is done, then fabrication, again during the fabrication also one has to be it has to be properly quality controlled. It is so once that you do all this fabrication, then there is a specified testing, although testing need to be done to see that whether the testing are done by simulating the space condition environment, space environment. So, once those testings are done, then you have to do so one is testing, but that is always it is not possible or sometimes it is not possible to simulate exactly the space environment. So, you do the testing, limited testing, and at the same time the mathematical modeling or analysis also need to be done. Whatever we studied, the mathematical modeling, this also needed to be done. So, a good design, then you do the testing and you do the analysis. These things, all these things will ensure that and then if you take all the measures, like we will come to that, how to select the material and all this thing. If you can do all this thing, then the spacecraft will become resilient against the effects of charging. Charging will happen, but this spacecraft you can design it in that way, so that the spacecraft will work, the subsystem will work for the designated period of the the mission. So, what are the design practices? So, there are some the guidelines. First is the shielding. So, the spacecraft is shielded like from these energetic particles, it should not come inside. So, that is why there is a guidelines how to use the shielding material, like the metallic shielding like aluminum or the titanium or different types of alloys, how to use it, what should be the thickness, so that those energetic particles or the radiation they do not enter the hull of the the spacecraft. So, these are called the shielding. Then other thing is the bonding. There should not be anything isolated, like if the circuit, there should not be any isolated parts, even the structural members, everything should have a proper bonding. Okay. So, this bonding is very important. Then the surface materials. So, whatever the surface materials are used, we will see that you have to choose their you should know the properties, and as for example, suppose the outgassing is not only the contamination, but it those contaminated particles also may get charged. So, what is the outgassing properties, what is its secondary emission yield, all these things there is the specified the specification, those specifications need to be satisfied, and there will be an approved list of the materials. So, which will satisfy those properties. Then this surface materials, everything, then again this need to be bonded to a common ground of this spacecraft, so that they are not isolated, electrically isolated. Similarly, the all the wiring and the cable shields. So, the shielding it is called the casing. So, suppose you are using for a particular subsystem, you have shielded it, then whenever this wiring and all this thing it will come out of that shield. So, there also those everything need to be shielded and the proper bonding, all these circuit cables, everything should be bonded to the spacecraft common ground. So, this is also same, that you should have all this subsystem, that is electronic subsystem or electrical subsystem, all these things need to be grounded to a common ground of the spacecraft. Then material selection, already I told about that. Material selection will be those materials which are in the approved list, which satisfies all this this, or it is called the space qualified, which are qualified so that it can work in the space environment. So, those material also only you can use. Now, analysis. So, analysis already we in the last few sessions we are discussing that analysis part only. So, you can do the analysis and you can predict what will be the the how much the spacecraft will be charged, what will be the potential, all these things can be analyzed and can be predicted. And there are different approaches. One approach is that you can use a simplified analysis, where you can take various types of assumption. You can take the spacecraft to a very symmetrical one, you can consider a spherical, all these things can be done. But if you want to do a robust analysis, then this computer code, the numerical methods and the all the models is need to be the physics based model, that using the plasma physics. What is the trajectory of the charges, what is inside the spacecraft sheath, what is the trajectory of the particles and how it is interacting with the spacecraft, and then finding the equivalent circuit as we have shown you. So, all these things need to be done. So, that will be a robust numerical code. There are codes, numerical codes available commercially like NASCAP, then Spacecraft, then one is Muscoet. So, different codes are available. So, those things need to be used. Now, testing. So, whenever I said a material is space qualified or it is there in the approved list, suppose a material is I have a new material, it is not included in the approved material list. So, it need to be tested for it needs to be tested for the various properties, like what is this outgassing properties, then what is it the shielding, what is its the secondary yields. All these material properties need to be seen, and then you have to find that okay, yes, this material can be used, it follows all the the material properties. Then whenever the circuit and components, that also need to be tested. Once is the material testing, then the testing at circuit, even at the component level. Like I have an suppose a connector, or I have to use for a particular power level. So, we need to see that connector is qualified or not, whether it can withstand that much, whether there is any gap in the, suppose in the connector there is some gap. So, there can be some discharge. So, all these things need to be tested. So, you will be able to know all these things whenever we do the component or the circuit testing. Then once we assemble, suppose a subsystem is assembled, then that assembled systems, their subsystem, the subsystem can be an amplifier, or it can be a frequency generator. So, there are different types of subsystems. So, those subsystems are made by using different components. So, when it is integrated and you have made the subsystem, so it need to be tested. So, when all the subsystems are qualified, then they are a system is made, like a payload is made, then that payload need to be tested, and of course, after that satellite is also tested. So, this once you do all those testing by simulating this space environment, then it helps to define the level of risk. Then you will be knowing what is the what is the reliability, that we will do a chapter on or a module on the reliability. You have to assess the reliability. What is the failure rate? Suppose I have tested some 1000 components, what is the failure rate, and then we can assess what will be the reliability over the time. So, these are the way, if you do the testing, it can be done like it will help to to the risk assessment, and it will give an confidence, okay, the components will work for 10 years or it will work for 15 years without this much of the degradation of its performances. Then inspection is very important in while the developing the there is a whole process of the from starting from the drawing generation to fabrication, everywhere the inspection it comes under the quality control. So, the inspection is very important, and it gives you it is a means for recognizing and minimizing the possibility of the spacecraft charging, and especially the the discharge induced anomalies. So, here this all the inspection generally it is need to be done at the when the spacecraft is being assembled, and this needed to be done by the inspector or those person who are experienced in recognizing the likely areas of concern. like whether there is any floating, suppose the circuit is a floating, it is not grounded, or whether a particular joint is whether it is bonded or not, all these things need to be assessed or need to be inspected, and then once the inspector will certify, then only you can proceed, otherwise this need to be corrected, and then only if something is found that is not properly done, so those things will be implemented. So, that is why inspection is a very important the activity of the quality control. So, for the quality assurance. So, these are the different the what are the, there will be the inspector, he will have all those like the resistance in the joints. So, maybe you need a low resistance path. So, that need to be seen whether that particular the bonding is whether it is satisfying this whatever the acceptable values or not. If it is not, then it need to be corrected, and generally this inspection it take all the possible areas of concern. So, what are the mitigation techniques? So, generally this mitigation or the solutions, there are two types. So, first you prevent the build up of large potentials by actively balancing currents to spacecraft surfaces. What do I mean by that? So, what you do, you proper there is all the system, it should be connected, there should be a conducting path. Okay. So, even if some dielectric is using, so the dielectric should have a good the electrical conductivity. It should not be that we have a very good insulator will not be a good candidate for when I consider the mitigation against the spacecraft charging. So, and you have to prevent differential charging of the surface by ensuring that the entire surface is of uniform conductivity. So, that also need to be ensured. Okay. So, what are the recommended the guidelines for the the control of spacecraft charging? So, as we discussed, the first one is the grounding, proper grounding. There should not be any any subsystem which is in a floating condition, it has to be grounded to the chassis or the spacecraft, the common grounding. Then you are to that the surface materials whatever you are using, those materials need to satisfy all those the properties like outgassing properties, then what is its this yield coefficients like SUI, BUI, all these things need to be see. Then the shielding is essential, very much essential when if I want that if I want to stop the internal charging. Then proper filtering, suppose if suppose some discharge is there, some noise is generated, some this some higher frequencies or it is called the intermodulation signals is created. So, that need to be filtered, and then there are some this procedures or there are some this the guidelines or the how to do the assembling and all this, there are the that procedures need to be followed. So, as I already said that grounding all conducting elements to a common ground, it will minimize the potential differences. So, this and you make all the spacecraft exterior surfaces at least partially conductive, which minimizes the differences as well. Then shielding electronics and wiring and filtering the input to circuits, that already I said, and this will protect the spacecraft from discharge induced currents. And this processing whatever I am saying, so it is the finally it is proper handling. So, everything there will be there is a guidelines how we have to handle it, in what way you have to. So, there is the guidelines for the handling, then storage will also how you have to store it, then the assembly, then inspection. So, all these things they will ensure whether the proper electrical conductivity is there or not, and this will minimize the possibility of the adverse this interaction of the plasma environment on orbit. So, now these are all this passive way of controlling or so there are some active way also it can be done. So, we will discuss that. So, in order to prevent the buildup of large potentials, so a spacecraft may fly a plasma generating device. So, this is called the plasma contactor, which I mentioned in some slides. So, what is that does actually? It effectively it reduces the the plasma accumulation. So, how it is does we will just, so it is said that it is effectively ground the spacecraft to the plasma. So, basically the spacecraft has developed some potential with respect to the plasmas. So, plasma you are considering like zero potential. With respect to zero potential, suppose the spacecraft has got some few kilovolt, it can be some 20-30 kilovolt. Then this can be minimized by using, this is the active method, this is called the plasma conductor. So, what is that actually? You are producing this produces a very low energy plasma. So, low energy plasma. So, this spacecraft may reattract the plasma species of opposite charges. Okay. So, what is happening actually, suppose if the spacecraft is negatively charged. So, now if you use generate some low energy plasma. So, what it will do? It will the reattract the the opposite charges, so that it the negative potential it will increase. Basically what is the goal? Goal is that to get it is grounded, means it has to be also 0 volt. So, this can be done by using this type of thing. So, what is done actually? So, a similar effect also can be it can be used by the ion thrusters or the plasma thrusters. So, plasma thrusters also can be used like a plasma conductor. So, what the plasma conductors they do? So, it limit the maximum charging potential. Okay. Suppose it is minus 20 volt, it can bring it to some few volts, but for that they will require the additional weight, power and cost, and they will add to the complexity in the design. So, we will see wherever it is absolutely necessary, this type of active control or the plasma, you can control the plasma using this type of active devices. So, this International Space Station, where it's this reliability is of extreme importance. So, there it carries the plasma conductor and it is fueled by xenon that is designed to limit the maximum floating potential of the ISS to about minus 40 volts. So, you see this is quite a benign one. So, this all can only be done when you use this type of plasma conductor. So, if when you compare against the cost of the the changing the electrical and the electrical power system design, and sometimes there is a technique like the power system, the grounding changing from from negative to the positive ground. So, this also gives a mitigation technique. So, you can do that way also, or the changing the design and the manufacturing of this structure to utilize the thicker dielectric anodized aluminum coating. So, it again it depends on this some cases. So, in this case you can do this the mitigation techniques, like as I said, by changing the power system ground, or you can change the design and manufacturing of this structure. You can use a very thicker this the dielectric material you can anodize with the aluminum coating, and then in that case the plasma conductor, especially for the case of ISS, it is a affordable solution. And we can there is a there is a great, or it is a there is a similarity between the plasma conductor and a plasma thruster. The plasma conductor, it is tailored to provide current, So, as I said, a low energy that it generates a low energy the plasma, which will attract the some plasma species which will recombine with the spacecraft this accumulated charges, and it will reduce the potential. So, basically it is tailored to provide current, while this thrust, a plasma thruster, it is tailored to provide a thrust. Okay. So, this this purpose is different. So, plasma thrusters, it can be used in geostationary orbit for the station keeping, but if available they may help to discharge the vehicle during the periods of intense spacecraft charging. Now, the differential potentials, it can be minimized by making the exterior surface of a vehicle as conductive as possible, and solar arrays, it may be coated with transparent layers of indium oxide or indium tin oxide. These materials are conductive. So, this method was it was used in that ISEE, that is International Sun Earth Explorer spacecraft, because the scientific instruments of the vehicle would have been affected by the built up of the differential potentials. So, as I said, these instruments are for the scientific exploration. So, it is needed that this the charging should be as low as possible. There should not be any the differential charging. But again all these techniques, they will add the weight and the the cost, the expense to the vehicle design. So, as I said, the active methods, that is the plasma conductor or the or conductive coating, of course, this is the passive, are only used where the significant problems are foreseen. Like for the low Earth orbit, this the effect of the spacecraft charging is much benign. That is, we already discussed that there it can be some few balls, it can be 100 ball, minus 100, minus some cases it can be minus 400 or 500, but that will not give rise to a discharge. So, generally the discharge effects are there in the high Earth orbit when the magnetic storm occurs. And the composite materials, that is the CFRP and all those materials which are used, and there can be they are all these materials like CFRP is conductive, it is. So, this will minimize the differential charging and provide a common space ground. So, this is all about this module which we are discussing the plasma environment. So, before we go to the next module, so next module will be the radiation environment. We will have in the next session, because we have done we have given you various the formulae for calculating various plasma parameters. So, we will solve a few problems in the next class, and then we will proceed to the next phase, the other type of space environment, and we will study the radiation environment. And with this I am concluding here. Thank you very much.